Hi, everybody. Thanks to the DataBeers organizers for having me again here. It's a fantastic event, probably one of the best data events around. So I've been working on data for several years already, and in the past few years, I've had the privilege to gather people that work with data around what I believe are really nice and interesting projects. So I'm going to talk to you about the most recent one. Okay, we call it anaerobic data. So there's a few very, very interesting databases in the world. Not so many, you know, the telco data, governments have very nice data, healthcare data. And not many times one has the opportunity of building one from scratch. And when you say 1 meter resolution of the whole planet updated every day, that sounds like a very interesting data set that we are trying to build. Of course, there's a lot of other location data already, and some people might say, why more? Why more satellite data? If you look at these are images taking over a year in the world, so one would say you have the whole world covered. Why do you need more data? And it is true. There's a lot of problems that, thanks to location data in the last 10 years, have been solved. Our telephones have over 9 different ways. Any normal telephone has over 9 different ways of measuring location, right? So it seems to be a very important piece of data. And the fact that many of us came here and we knew at what time we would arrive at the minute is something that was unthinkable of only 5 years ago. But also, if you look closer into that map that I just showed you, that seems to be completely covered, you find out that this is very spiky, and that we have a lot of data where people are, and people are not in many places. Actually, urban areas only cover 1% of the world. So what you have is something like these. People take a lot of pictures in Paris, and then you do that heat map, and you do a Gaussian on it, and you think that you're covering half of France, and it's only the Eiffel Tower, right? So there's a lot of problems that are not solved in that required location. And these are some of the problems right here that are still far from being solved, basically because we're not there. And we don't know if the tree makes a noise when it falls if we're not there, right? So here, one of those problems, which I think is a pretty important one, is how we're going to feed 9 billion human beings by 2050. And the options we have for that is either increasing farmland, as we've done in the past years, basically throwing down forests or irrigating deserts, which sounds not very environmentalist, or betting more on genetically modified crops. There's another way, which is basically doing what we're doing today much better. This kind of data, if you have every day a picture of your farm with 1 meter resolution and with multispectral or even hyperspectral sensors, you can use that data to take decisions much more precisely, pretty much in the same way retailers do these very advanced customer segmentations to bomb us with advertisement. You can do a farm segmentation with that data, much more precise, and decide how much you will irrigate, how much nitrogen you would throw in different parts of the farm, and so forth. Here's another problem, deforestation. Until not long ago, we wouldn't even know where forest would change in the world. And thanks to the data that we have, but especially thanks to the capability of analyzing all that data. Look only at the data for the forest case, how much the size of the data, the size of the problem. We're able to see deforestation now, and even better, we're able to predict or even to prevent deforestation. So one of the issues with Earth imagery is size. Right? Landsat, which is probably the most well-known repository of satellite images, 1.3 petabytes. But Planet, which now has several satellites out there, already has 7 petabytes in their archive, and it takes them just between 3 and 6 months to have another Landsat archive. Right? So they're growing really fast. The reason you're growing fast, if you plan to take an image of the Earth every day, then you're capturing 510 terapixels, half a petapixel. Every day, that's about 400 terabytes per day, right? And that's only if you're doing RGB images. And a lot of these sensors capture multiple spectra, so you multiply that by the number of spectra, and you even want to increase frequency. So you have a huge problem here because the amount of data that you can capture is much more. It grows much faster than the amount of data that you can download from the satellite, simply because of the physics of the communications and the things you can do with communications, right? So, and not only that, when you're working with satellite data, a lot of the solutions to the problem rely on you not only working with the satellite data, but combining that data with different sources. So you can combine with demographic data, with topographic data, with geologic data, or with even human related data. Here are some of the sources that we built for our own experiments. They can be public data, it can be data you buy, like elevation, it can be stuff that you've seen here in DataBeers. On each one of the sessions, probably practically one of the maps, credit card transactions, telco expenditure, population density. You can derive stuff, you can save some work to the neural network by just saying, well, mountain orientation seems to be good, so I'll compute it first instead of throwing it to the neural net for the neural net to learn. And when you have all these layers of data, you can start doing this kind of stuff, which is basically you have land use, for instance. Here's a picture of our own picture of Sabadell. And here is some of the typical land use categories, urban areas, agricultural areas, and you can start classifying. That's the basis, because that's how you teach computers that use satellite data to speak. They start speaking our language if you tell them the semantics. And on top of that, you start building things. So land use, land cover, that's a basic dictionary, right? And then you can start doing stuff like this, because you have a map, and then you see that you took this image, and some things are uncharted, so you can see change detection, what's happening, how construction is growing or decreasing, what's the different types of land use. Imagine that you would be able to know, for instance, we would be able to know the exact amount of soybean that is planted in the whole world every day, and tomorrow, the difference tomorrow. So here is one other application. These are the typical applications. The first applications that we're seeing are basically object detection and classification, right? And there's somebody who said that if you were able to detect how many cars were surrounding Walmart, you would be able to bet much better on Walmart stock. So there's a lot of companies just counting cars to do that, which is kind of silly, because you can count cars in much more efficient ways than from satellite images, but there's a lot of nice applications around that, and there you can see the response of a neural net that's trained on cars up here. But it gets each time more interesting, because there's some indicators, some global indicators, that just because you have this data, you can start inferring, and for instance, that have nothing to do with satellite images. So for instance, there's some very nice studies on inferring poverty, which is a not so well-known indicator, especially in some regions of the world, from the illumination, from night images, like this one. And it's getting better over day by combining it with other sources. And it gets better because some people are starting to do more advanced similarity search, for instance, for images. So if you train your system on, in this case, windmills, energy, you can find the location in the map for every single windmill by just showing the system a couple of samples. And you can build those indicators, like you can find the total amount of renewable energy that's being generated in the world at any point in time. And it gets even tougher. And some of these things are not solved yet. So I'd like to just wrap up with two of the problems that I believe are interesting and they're not solved yet. And one of them is that there's a strong asymmetry of ground truth in the world. And for instance, these are olive trees in Spain. And so one would say, oh, we can track olive trees in Spain with satellites, and you think that's a great idea, and you soon find out that every olive tree in Spain has a chip. So, and it knows the health of the olive tree, and so why would you? But the interesting point is that that is also data from which you can learn about the olive tree, and you can cross that with the images that you gather, and you can check out the health of the olive trees in Morocco or in Chile, thanks to that. Okay, so these are very nice problems of how to transfer knowledge that you have in one region of the world to another region of the world with possibly very different conditions. Very nice challenge. And the last challenge is the one I told you about, right? We're talking about many satellites going up in space and a large number of satellite images coming down, but there's this communications constraint. So what I think is that as we move forward, we'll have each time less satellite images coming down and each time more satellite constraints, satellite insights coming down, thanks to not only doing the anaerobic data part, which is capturing the images, but also doing the anaerobic data processing part by equipping these satellites with the power to process all that information. Thank you.